Hello, my name is Andy Hales at the University of Mississippi, and in this video we're going to look at how to calculate power for one-way ANOVA designs and some of the comparisons you might do afterwards. So we're going to use an R package called Superpower, so go ahead and get that loaded up. The great thing about Superpower compared to other alternatives like G-Power is when you are planning a design with a one-way ANOVA, you care about the power for the omnibus effect, but you also really want to be able to say something more specific or useful beyond that. And the superpower package includes power for specific mean comparisons afterwards. Now, it's a little bit back of the envelope. You can't do specific planned contrasts, but you can get a rough estimate of power for pairwise comparisons. And at the power analysis stage, since you're not omniscient and you don't know the population effect size anyway, this back of the envelope estimate is good enough to plan a study at least. So let's start with just a basic situation where we have three conditions and we want to know the power for an overall f-test, but also the power for comparisons between them. So what we're going to do is we're going to set up our design using this information. We're going to save that to an object called design setup, and then later we're going to feed that into this other function. It's a little tedious, but it works. And down here is where we'll actually calculate power. But first, let's input all the settings the way we want them. For starters, it needs to know what our design is, and our design is three conditions between subjects. Whoops. So we enter 3B here for a three condition between subject design. We also need to give it our sample size. This is n for each condition. So we're going to imagine here that we have 300 participants total, 100 in each condition. Now, you might be in a situation where you anticipate different numbers of participants in each condition. I'll show you how to do that at the end. For now, 300 total. Next, we're going to entertain some possible mean differences in the population. We don't know the population, but we do want to estimate what our power would be if we ran 300 participants and if this is the situation in the population. Now, to keep things simple here, notice what I've done. We need to give it the three means we expect for each condition and the three standard deviations we expect for each condition. Now, if this is a direct replication, or if I've used this measure many times, I may know the exact means and the exact standard deviations. And in fact, if I'm planning a confirmatory hypothesis test, hopefully I have used these measures before and I have some sense of how they behave. If I don't even know how my measures work, it might be too early to test a hypothesis. However, if you want to simplify things by working in the world of standardized effect sizes, a very easy way to do that is by telling R here that the standard deviation is 1 for all three of your groups. And what that lets us do is it lets us enter a pattern of means whose differences are in units of Cohen's d, standardized mean differences. So what that would mean in this case is we can imagine that the mean for the first group is 0.3, and the mean for the second group is also 0.3, and the mean for the third group is 0. Well, if that's the case, then we're saying the first two groups are a third of the standard deviation higher than the third group in the population. If we want to calculate power under that assumption, this is how we would do it. Finally, we have label names here if you feel like inputting the specific conditions for your study. It's kind of a cosmetic thing, but especially with factorial designs, it can make things easier on the eyes, so you have the option to do that here. For now, let's go ahead and run this design setup to see what we're working with. And a really convenient thing about Superpower here is it'll show you a graph of the means that you've input, so you can confirm for yourself if this matches what you're intending to do. And here, yeah, that matches what I'm intending. I'm saying let's suppose that these two conditions are a third of a standard deviation higher than this other condition. That's not so crazy. A lot of effect sizes in psychology are in the ballpark of a third of a standard deviation. If that's the case, then I can say with 300 participants total, how often will I get a significant omnibus effect? Okay. but also how often will I be able to detect specific differences between any two of these means. So we can now go ahead and compute exactly that. So what I've done here is, do you see, we're going to run ANOVA exact, and the first thing we tell it is the name of this object we created up here called design setup. So I set all my values up here, then down here I give it the name of this summary of all that, and of course I can set my alpha level here. We know that affects power. Here we'll set it to the traditional 0.05, and when we run this, we save a new object called power result, and when we print that, we at the top here we see the power for the ANOVA test, and with 300 total participants, if the population pattern of means is 0.3, 0.3, and 0, well then we will walk away with a significant result 58% of the time. Not great. Now this also computes for us what the partial eta squared for our omnibus test is, and that is 2%. Explains 2% of the variance. And it also can express that as Cohen's F. If you've ever worked in G-Power, Cohen's F is the effect size for an omnibus test that gets used. Something to be aware that you can find it here, but not immediately important for us to interpret the result. Now, a partial eta squared of 2%, that might not sound like a lot, but do some experiments and you'll see. Often that is the size of the effects we get when we're testing hypotheses in social psychology. Now we also get down here power for each of the specific pairwise comparisons. And in this example, it's not applying a correction. You can apply some corrections. Tukey is not an option, but there's others here. So if you wanted to go through the menu and find the closest, you could. Because this is back of envelope for now, I'm just seeing what this would look like. And power for the comparison between condition 1 and condition 2 is 5%. Well, that's because they're identical to each other. So any difference you get there would be a type 1 error. So when we see that power is equivalent to the type 1 error, right, that's why. And then for these other comparisons, condition 1 versus 3 and condition 2 versus 3, we can see we have just 56% power to detect that. And the effect size is the Cohen's d that we entered of 0.3. So on its own, this is not a promising design. I would look at ways to increase the effect size or increase the sample size before proceeding with a study like this. Now, in superpower, unlike the earlier t-test power that we used, you can't input 2 of the 3 values to compute the third. Instead, you just have to tinker with these options in order to answer the questions that you want to answer. So for example, suppose I wanted to know what sample size would I have to run in order to have 80% power for an omnibus test. Well, there's nowhere for me to enter power here. So instead I have to use just a little bit of trial and error by inputting different sample sizes until I find the one that corresponds to 80% power. So I could say, what if I run 150 per condition? Well, in that case, all right, that's up to 76% power. So maybe it's 155 per condition. Pretty close. Maybe it's 160 per condition. All right, that's, if you round up, that's 80%. So you see how I can sort of trial and error my way to answer a question about a priori what sample size would I need to have 80% power for an omnibus test. I could do the same thing for specific contrasts if I wanted. You could also use this menu of options here to do essentially a sensitivity analysis by saying, you know, if I were to run, let's say, 200 participants in each condition for 600 total, what effect size would that give me 90% power to detect in the population? Well, we can start by running this, and we see that with this current design, wow, well, we have about 88% power to detect this pattern where we have 0.3, 0.3, and 0. Now, my question a moment ago is what would the effect size have to be in order for us to have 90% power? For the example, let's say it's 90% power for a particular mean contrast. Well, we know the effect size would have to be bigger than it is here, so let's entertain that the population effect size is not 0.3, but actually 0.35, compared to the third condition of 0 here. And if we run that with 200 participants, we see that's a little higher than it needs to be. So again, using some trial and error, what if the effect size is 0.32? All right, well, that's a little low, so maybe it's 0.325. Here we're getting really more precise. All right, there you go. So that tells us that with 200 participants per condition, to have 90% power to detect a specific mean difference, the population difference would have to be 0.325. So you have to go about it sort of indirectly here, but I hope you can see that you can answer the same questions just by inputting different information and using a little trial and error to get to what you want to answer. Okay, so that is how you can get a pretty good sense of omnibus and specific contrasts, or specific, I should say specific comparisons rather than contrasts, because these aren't proper planned contrasts, but they're back of the envelope and definitely better than what G-Power will give you, at least in terms of convenience. Now, I mentioned that there might be situations where you expect to have different sample sizes per group. Maybe you have one group that you're especially interested in learning about, so you overassign people to that condition experimentally, or maybe you are studying conditions in the population, you just have access to more of one group than another. Well, in order to do that, you set up the design, and here, instead of giving it just one number, you give it 3 numbers corresponding to the sample size for group 1, group 2, and group 3. So in this case, we're imagining we could run 400 participants, 100 in group 1, 200 in group 2, and 100 in group 3. Superpower can handle that. However, unlike before where it can just do the computation and give you the result immediately, here it answers this question by simulating many data sets and then counting up the number that are significant, and that is by definition power. So down here, once we've set up the design the way we want, instead of using ANOVA exact, where it exactly calculates power, we're going to use ANOVA power, which simulates it. So it'll take a second to run all the simulations, but the advantage here is if you really want to know about power for situations where you have a different n per condition, this lets you do that. So here we give it, again, the name of our design that we set up, and we can tell it the number of simulations. 1,000 is a fine starting point, but if you want to be more precise, increasing this to 5,000 is pretty good. There's probably not much reason to go above that. It just takes a little longer. So for the sake of this example, you use just 1,000, and you can give it a seed to get the same result each time if you want to make this reproducible for someone else to check the work. So here we can run this and view the result, and right now the computer's thinking, still thinking. Can go get a sandwich. All right, well, there's the result. In this case, we have 64% power to detect this an omnibus effect with this population pattern of means and these sample sizes. And here for the specific comparisons, again, the means for group 1 and group 2 in the population, we are already told it that's identical. So power here is right around 5%. Now you'll notice it's not exactly 5% because we're using the simulation method. So if we increased from 1,000 to a higher number, well, then that would more precisely estimate 5%, but it's a good estimate as far as power goes. Here, comparing condition 1 to condition 3, we'll get a significant result 58% of the time if these are the population mean differences. Now remember, group 1 and group 3 in this example were the smaller groups with 100 each. But we told it that group 2 is going to have 200 participants. And it looks like that improved our power for the specific contrast between group 2 and group 3 all the way up to 68%. So this gives you a little more flexibility. If this is something that you want to incorporate into your design, you can answer more questions about how to do that here. So there you go. That is how you use superpower to answer some questions about what you can reasonably expect to produce significant results under different design conditions. So there you have it. I'll see you next time.